Interesting. Okay. So at the top there that I gave you, notice I said solids can either be amorphous or crystalline. So that's the top thing of the logic tree I gave you. And then it goes on, under crystalline we have a lot of different options. Okay. Crystalline solids, as the word implies, you kind of have, you think of a crystalline lattice structure. That's kind of what we have, nice and organized. Okay. And if they're organized, they tend to have other issues, a little higher melting point. Amorphous solids, I'm going to show you, I have two examples. Plastic's an example of a good example of amorphous solid, and glass, just plain old glass, like window glass, is another example of an amorphous solid. They aren't organized, they're kind of willy-nilly, okay? So I mentioned plastic is a good example of something that's an amorphous solid. All of these others over here are types of the other type of solid, crystalline solid. Okay, network solid, metallic solid, ionic solid. Those all fall under crystalline solids. See what I mean? A lot of terms there. Okay, so starting with a molecular solid, which is a type of crystalline solid. Okay. The term molecule comes to mind, I don't know. We talked about different ways of letting molecules connect with each other. Okay, we have the dipole, induced dipole. That would be the dispersion forces, or special hydrogen bonding like water. Okay. They generally melt at a relatively low temperature, and unlike some of the other solids we're going to talk about, they do not allow electricity to pass through. They have a high resistivity. They're poor conductors of electricity. So you might recognize the cute little water molecules, all organized in solid state, as I look out the window and it's totally snowing out there. Okay, so when water is in its solid state, that's an example of a molecular crystalline solid. Okay, another type of crystalline solid is a network solid. These, unlike the molecular solids, are generally melt at a higher temperature, but like the molecular solids, they don't have free electrons to let the electricity pass through them. We talked about the, what was it for carbon? It's not isomers, it's the different forms of carbon. Allotropes. There's another vowel, allotropes. The different allotropic forms of carbon. So we have graphite, diamond, buckyball. Okay, but in its carbon bonded together in its in the form we call graphite, looks like this. Looks like a network crystalline solid. And each one of those little balls there are carbon atoms again, but they are a different allotropic form of carbon. Diamond. It's a high melting point temperature. Quartz is another example. To me, I mean, here a close-up of what quartz looks like. It's like the repeating unit is 1 silicon and 2 oxygens, but boy, it's hard to see up there. Okay, high melting point temperature. Then we get into something actually we talked about in Gen Chem 1. The ionic compounds would be this ionic crystalline solid, like sodium chloride, where an electron is entirely transferred from the metal to the nonmetal. You end up with a cation and an anion, and they're stuck together by, like this says, Coulombic forces. They still do not conduct electricity in their solid state, but do you think salt water conducts electricity? Yes, it definitely does. But sodium chloride solid does not conduct electricity. High melting points. So there is sodium chloride, the alternating cation, anion. We did call that a crystalline lattice structure before. So that is the ionic crystalline. So that's the second one here. See, I just got confused. I'm like, well, what is that? That's not amorphous. It's all under this crystal. Sodium chloride again. Those bonds are very strong. Then we get to maybe even my favorite, the metals. And metals have a very high melting point. And melting point is an indication of intermolecular bonds, but not as good as melting point temperatures. A high melting point temperature is not as good of an indication as a high boiling point temperature of what sort of intermolecular bonds are going on behind the scenes. But this talks about a sea of electrons. That is so cool. I meant to bring like a little copper wire. Just picture a little copper wire. And picture basically, if we pick on copper, put on your Gen Chem 1 hats, pick on copper, and look, copper on the periodic table is, looks like it's a D block element, okay? And the valence electrons, actually, it's only got 2 valence electrons. It's got these 2 valence electrons. This looks like it's in period 4, so there'd be 4s2. These two, this is actually 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9. If it's in the configuration, lowest n plus L rule. So these valence electrons are just kind of delocalized and available to move. Isn't that cool? I just think that is so neat. So finally, this is the type of solid, because its electrons are delocalized, that it really does allow, you can push electrons through. Make an electron gradient. High electrons, low electrons. Okay. The other thing about metals, we know that you can, ductility means you can spin them in a wire. Malleable means you can hit them like with a mallet and flatten them out. That's unlike like sodium chloride. You whack that and you got a mess, right? Okay. So here's a picture to kind of show you the pluses are that would be like the copper atom. The pluses are like the copper atom, and it's got a plus there because basically its 2 valence electrons are swimming around. That is just so fun. It's like playing musical chairs. Okay. So I already said melting point temperatures, the temperature at which something melts, is not as good an indication as the temperature at which something boils with regard to what sort of intermolecular bonds we have going on. But I'm hopefully going to show you a couple of videos of things melting. You're like, oh, things melting. But if you look closely at it, and actually the melting point temperature is when you take organic chemistry, the temperature at which something melts is an indication of its purity. Of course, the temperature at which something melts is an indication of what it is. Okay. The range at which over which it melts is an indication of its purity. So if you're looking at something to melt, basically you jack up the temperature little by little and you look for it to collapse, to go from a solid to a liquid. So cool. This should play for us. To the number of the strength of the intermolecular bonds and the number of intermolecular bonds is actually, it's the symmetry of the particles that are stuck together as a solid state. So in general, and this might help you out, I don't know if it was a word you had to fill in, but with symmetry, or the more symmetrical the molecule, okay, that means they fit more regularly together, and that requires more energy and will have a higher melting point temperature. So look for symmetry. If you find symmetry, you would expect a higher melting point temperature. I think I'm going to skip those videos for now. So let's look at an example. Do you remember the other day when I was up here and I went something like this is trans and this is cis? I don't know if, okay, maybe not. So these two compounds have the same formula. 2 carbons, 2 chlorines, 2 hydrogens. And I think I mentioned the other day, anytime you have a carbon with a sigma pi bond, so carbon double bond carbon, there's no rotation around there, okay? And the other thing is if you look at the other things that the carbons are connected to, basically you have sp3 orbital hybridization, which means you have trigonal planar on both the carbons. Both of these lie, I could take a piece of paper up there, and they both lie on a piece of paper. They're planar molecules. Anytime you see trans, I always think trans is opposite, okay? So in this case, the trans version, we mean the chlorines are opposite. Okay, the chlorines are opposite, or the hydrogens are opposite, okay? Over here, this is the cis version, okay? Chlorines over here, on the same side. They are different, they behave differently. So one of the things we've talked a lot about is polarity. And I'll just go ahead and reveal who's polar and who's not. So they lie in a plane, and let me kind of emphasize, do you see where chlorines, Pauling says chlorines have a very high electronegativity, okay? So this is going to be, see, I won't put a partial there. I'll just put, this is negative, and this is negative, and this is kind of, these are kind of like, yeah, these are kind of like neutral. They lie in a plane. Can you see where the center of that negativeness is right here? Okay. The center of that negativeness is right there, and actually that's the center of everything. So basically that's why it's a wash. Okay, the positives and negatives. Okay. Well, let's look at that. Let's take that same idea and look at this one. Negative, negative. Let's kind of ignore carbons and hydrogens for now. Where's the center of negativeness there? This is the center of negativeness. Now, you might not know what the carbons and the hydrogens do, but let's just say they're neutral. Can you see where that does have a net dipole moment? Okay. It's going to be, and if we go ahead and use the vector where you use the top of the arrow is where the positive is, and then where the arrow ends is the negativeness. It's got to have a net dipole moment. So mu is not equal to 0. It makes it polar. So which one should, how many people, we'll start with this one, we'll go this one, the cis and the trans. Let's see, higher boiling point temperature. How many people think that the cis should have a higher boiling point temperature? You are right. Give yourself a pat on the back. Perfect. Very good. Okay. So with that trend, this is where symmetry enters in. With that trend, if this has a higher boiling point temperature, you would think it would have a higher melting point temperature too. Melts at a higher temperature, more intermolecular bonds to go from a solid to a liquid. Okay? I'm going to show you that's not the case. Instead of a higher melting point temperature, actually this has a lower melting point temperature. The one that appears to be more stubborn to melt, I know negative 80 is pretty cold and negative 50 is pretty cold, but the one that's more stubborn to melt is this one. That's not polar. So the previous slide, I had you underline symmetry. With symmetry brings higher melting point temperatures. So let's see if we can convince ourselves of a little extra symmetry here. If I go, well actually, I think the way this works is, if I make a dot here, can you see where on either side of the dot, I got 2 carbons here, okay? I got 2 hydrogens here, I got 2 chlorines here on either side of the dot. Basically, you have a dot of symmetry. Okay. I would agree, though, we've got kind of a reflective sort of symmetry here. okay? But it's not as stacking, okay? So basically, the reason this is higher is due to symmetry. Cool. So the last slide I wanted to knock out before we go on to talk about phase diagrams is this one. And this one, just kind of at a glance, if you kind of orient yourself, we're talking about those alkanes, those hydrocarbons that only contain single bonds. We're talking about the normal version, no branching. And basically down here, they're saying the number of carbons, okay? So basically, methane, ethane, propane, butane, pentane, hexane, okay? And we have the corresponding boiling point temperatures and melting points. Okay. Now, on to part 7. Yeah, there was a couple slides there, but the last slide's kind of pretty. It has a picture of broken glass, which is also, finally, another amorphous solid. Okay, phase diagrams. Each one of those dots is a different phase. They are actually, let me go back, they are actually called, sometimes called pressure temperature phase diagrams. Pressure temperature phase diagrams. And here's why. We always put the pressure along the y-axis and temperature along the x-axis. Increasing pressure going up, increasing temperature going from left to right. So here's your 3 colors: solid, liquid, and gas. Those are your 3 main phases. Can you see the Y in that? I often think, I tell students it's like a Y. So here it is. It goes like this. Kind of looks like a wishbone. Pressure, temperature, phase diagrams have that kind of Y thing going on. And they're unique for a particular substance. Each substance has its own pressure, temperature, phase diagram. Okay, so I said pressure increases going up along the y-axis, temperature increases going to the right. So, over here in this quadrant, do you buy this, that we have high pressures and low temperatures? High pressures, low temperatures. Think ice cube. Okay? And that's actually what we know to be the case, is matter tends to be in its solid state at high pressures and low temperatures. Okay? The in-betweeners, okay, with regard to moderate pressures, moderate temperatures, liquid. And if we look at the other extreme down over here, okay, high temperatures, something's generally going to be a gas. And actually that coincides with low pressures, just in general. Okay, another pressure, temperature, phase diagram. You see the Y, so be thinking solid, liquid, gas, right? Okay. We'll talk a little bit more about this one. If you look at the segment from O to C, so everybody find the segment from O to C. It would look like this. This is the segment from O to C. Actually, notice it's actually the corresponding pressures and temperatures between a liquid and a gas. When we've talked about equilibrium vapor pressures, that's the portion of the phase diagram that we're looking at. Okay. Let's focus then on O to B. O looks like a special point, doesn't it? It is. Okay, so here's from O to B, and notice that is between the solid gas phase, which is one of my favorite things. Okay, phase changes, actually there's this idea of sublimation and deposition. Sublimation is like dry ice when it goes from a solid to a gas, skips the liquid state. That's what that would be. Something goes from a solid to a gas, or a gas to a solid, we call that deposition. So to kind of, to remind you what that looks like. I usually call from solid to a gas, I call that sublimation. And a gas to a solid you could also call sublimation, but I like deposition. I always think of frost as kind of deposition. So that's the corresponding temperatures and pressures at which that occurs. Then find the last segment from the special point O out to D. Okay, so this would be between something being a solid or a liquid. And we're actually going to just, does that look like kind of straight up and down to you, that kind of that line? Sometimes there's a little bit of slant, we call a positive slope. That's more likely, okay? Versus some cases, actually water is kind of weird. Water has a little negative slope there between the solid liquid transition. Oh, by the way, I guess this is all for the for the element iodine. So iodine, remember, and it's is usually an I2, so this is all for iodine. So actually we have the correct data up there. All right. So that O there, the kind of the middle of the Y, is what we call the triple point. And I guess you probably see why we call it the triple point. Triple meaning three, so you have the three phases of matter kind of coinciding, coexisting at that sweet ordered pair. Okay, and so the triple point for this one has a temperature of 113.6 degrees Celsius and maybe 0.5 atmospheres or so. Okay, so one other important point on here, and it's the hardest one for me to explain. I was thinking, actually, you know how kids, there's so beautiful birds out there. Oh my gosh, there's like robins. Aren't those? Yeah.
Oh, wow.
I know. They're just like so many in one spot. So, you know how people like want to say, what's the fourth phase of matter? Plasma. And I'm like, oh, come on. So, all right. But to me, it's not another phase of matter, but actually supercritical fluids, which I'm going to describe using this phase diagram. That is, to me, another phase of matter, supercritical fluids. Okay? So we'll be talking more about that critical point, but actually it's abrupt end. It's always kind of at the left part of the Y, the right part of the Y. It's an abrupt end. So basically, we'll talk more about that. All right. So we talked about normal boiling point temperatures, and we said that was the temperature at which the equilibrium vapor pressure was equal to the pressure of the atmosphere in general, which is 760 millimeters mercury, 1 atmosphere. So here, this right here is what you guys have been using with your vapor pressure curves. Okay. So that's the normal boiling point temperature, the temperature at which it goes from will condense from a liquid to a gas. No, will evaporate from a liquid to a gas or condense from a gas to a liquid. And then the normal freezing point temperature you can pick off of the transition between the solid and the liquid. That same pressure. Okay, so the triple point, the point O on there. Okay, all three physical phases are in equilibrium. Can't remember what planet it was, but they were talking about the triple point of water. I was like, I have to look that up. But it's not just a temperature, but it's also a corresponding pressure. Okay, so it's like an ordered pair there. The critical point, okay, where the abrupt end of the vapor pressure curve, okay, that critical point has a corresponding temperature and pressure too. We call the critical temperature and the critical pressure. Go figure. All right. So you're going to see this here in a minute, but if we take a liquid and we have it closed up, so it's not open to the atmosphere. Basically, you're gonna see that liquid start to, at the top, go, and the liquid's here, over here it's open. Well, it's not open to the atmosphere, but here it's a vacuum and here's a liquid. You're gonna see it kind of start to kind of bubble up, okay? But at some point, basically, the interface between the liquid and the gas becomes kind of hard to see. You figure if your process is heating up the system of interest, okay, if your process is heating up, basically you are making that liquid less dense, okay, it's expanding, it's getting more kinetic energy. Some of it's breaking its bonds, going into its vapor phase. But at some point, the density of the liquid's gonna, the whole liquid's basically gonna be about the density of the gas that's evaporating up at kind of the headspace there. Okay, so that's kind of how that works. So when we talk about supercritical fluids, I'll go ahead and draw it up here. You'll be doing these for your homework. Pressure, could be atmospheres, millimeters of mercury. Temperature, could be degrees Celsius or Kelvin. Here's my Y. This could be a straight up or negative or positive slope. Solid, liquid, gas. I'm going to go ahead and extend this one up for basically ever. I'm going to go ahead and make an abrupt halt right there. That is the critical point. Okay, so here's how this goes from my understanding. Basically, if you go up and over, remember I said basically there's another phase of matter? This is an SCF, supercritical fluid. And under it, with the caption, supercritical fluid, what makes it so super is it behaves like a gas slash liquid. Supercritical fluid. Isn't that so fun? Okay, so this actually is a series of heating this system up. Okay, so I can't remember, well, maybe it'll say what the critical temperature is. Still below the critical temperature, and can you kind of see, they call this the meniscus, right? We call that the meniscus in lab, looking at kind of trying to get the meniscus on the place where we're supposed to get it, if we want using a graduated cylinder. But that last one over there is basically we have taken what was liquid and what was gas above the critical temperature. Now we have a test tube full of something else. Okay? It's supercritical fluid. And yes, it has all sorts of applications. So there's the critical temperature and there's the corresponding critical pressure. Did you get that one? Okay. So you can think of this abrupt end, this critical temperature, okay, as the temperature, what's it say? It says the minimum temperature at which the substance will go ahead and still be a gas, okay? Still be gas over here, but it won't be here. Regardless of pressure. Supercritical fluids, lots of applications. That whole kind of gas, liquid sort of thing. It has a density more like a liquid, but it can permeate stuff like coffee beans and decaffeinate them. So it has a viscosity to be sneaky like a gas. So just kind of a different sort of cat. Okay. And this is kind of going from left to right, heating a liquid. Liquid's down at the bottom there, above its critical. I must assume it's also above its critical pressure too, but above its critical temperature. All right. So, oh, here's for iodine again. This is the one that we looked at. Okay. This then switches gears. This is for, it doesn't say what substance it's for. But let's kind of, I'll say play devil's advocate, but let's do some moving around here. Okay, so for instance, the up arrow moving along the y-axis, notice we call this an isotherm. The reason is because we're holding the temperature steady. Okay, all we're doing is basically increasing the pressure. So it's very possible to take a gas, otherwise known as a vapor, and go ahead and pressurize it, and it liquefies at that temperature. And it's kind of like, think of the difference between a gas and a liquid. Liquids have more intermolecular bonds. Basically, you're making them get close together and they form intermolecular bonds. Okay? So you can go ahead and, that's condensation basically, isn't it? Condensing. Okay? Well, if you are, if you take again at the original pressure and move over here, okay, to above the critical temperature, I guess the point here is, if you are beyond the critical temperature, you go ahead and add pressure, add pressure, add pressure. It starts out as a gas. The best you can do is for it to become a supercritical fluid. You're never going to get it to liquefy. So let's just kind of finish that circle a little bit. Let's say you're up there above the critical temperature and you go ahead and you cool it down. Okay, that would be going this way, right? Okay. We can definitely go ahead and get it to liquefy. Okay. That's kind of a little jog around the phase diagram. Pressure, temperature, phase diagram. So this is for carbon dioxide. So this is kind of like what you guys will be doing with your homework. Things that are key to drawing this phase diagram for anything. One of them is the normal boiling point temperature and let's see, boiling point temperature and freezing point temperature. You know that if you find on its diagram 1 atmosphere and then look where stuff is. Okay, but do you see where the normal? Let's see this. The normal freezing point temperature actually is a sublimation temperature. Check that out. Okay, 1 atmosphere pressure. Okay. Yeah, 1 atmosphere pressure. Basically, it goes, and this temperature corresponds to the transition between a gas and a solid. What do we call that? Sublimation. Triple point, not too hard there. That's the middle of the Y. Triple point for carbon dioxide is 5 atmospheres, which is hefty, and a chilly temperature of negative 56.7. The supercritical point, the supercritical pressure, or excuse me, the critical pressure is 72.9 atmospheres. The critical temperature is a warm 31 degrees Celsius. Carbon dioxide is not too hard to get in a supercritical fluid. So here are some substances kind of grouped together. Down here at the bottom, and actually you'll be referring to this for one of your homework problems, it talks about non-permanent gases at the 25 degrees Celsius is basically room temperature. Okay. The other thing about this chart, please make sure you kind of get your wits about you, is this is in units of Kelvin. So basically you have to subtract 273 from that to get it in Celsius. Or jack up the 25 degrees Celsius to 298 K. That's easier for this one. So if we pick on 298 Kelvin, actually that, I'll put T is equal to 298 Kelvin. That distinguishes the permanent from the non-permanent gases. That's the tipping point. Basically, the critical temperatures of the permanent gases are cooler than that. The non-permanent gases have a temperature that's warmer than that. All right. More. No, you don't have to memorize any of these. Usually in intro Gen Chem, they're like, do I need to memorize? I'm like, what do you think? No. All right. Okay, so water. Water in its solid state. This is interesting. I was thinking about this in my office. And I've read a little bit about this. But, for instance, if you pick just pick I6, okay, in its polymorphic state of 6 instead of the normal one, okay, that means this is between the solid and the liquid state. So this is what its melting point temperature, melting point, freezing point temperature. So check that out. You know, it's just weird. Basically, it transitions from a solid to a liquid and a solid to a liquid and liquid to a solid. It transitions at a different temperature than normal. This would be, let's see, 1 atmosphere. This right here, switch colors. This right here is the normal freezing point, or freezing point of normal water. So anyway, okay, still sticking with water. This actually is kind of a little, this is a subset of what we just saw. I mentioned that water has what this negative slope right here, and this is kind of unique, I think. And it has consequences. It's between the solid and liquid state. So if we focus on segment P to Q, okay, so at P we go ahead and we let water be in its liquid state. Sorry, let it be in its solid state. Okay, and remember how in this class I don't know if we've done this class, but basically kind of think that it's like a plunger, kind of that silver lid thing can kind of go up and down depending upon how many weights you put on it. So let's go ahead and put pressure on, increase the pressure by putting some more weights on that little plunger thing. Put all those weights there. Okay. So according to water's phase diagram, at the isotherm, pick a temperature that's just so a little bit, it looks like a little bit warmer than freezing point temperature. Or sorry, a little bit cooler than freezing point temperature. Warmer, cool, a little bit cooler. You go ahead and you add pressure and it liquefies. So the classic example that's important for this phenomenon is ice skating, which I have done very little of. But if you picture a pair of skates, you have a blade under each skate, okay? So basically the full weight of the person is now on an area like this. You have a great deal of pressure, and heaven forbid you pick one skate up so you can go ahead and scoot, right? So you can conceivably have all your weight on a bar like that. So basically you're adding pressure to that ice that you're skating on, the solid ice, and it liquefies, just like that. It knows what to do. So when you skate around, instead of really, being solid skate on solid ice, you basically are creating a layer of water as you go. So I think that's kind of cool. And then, of course, notice they have, this is point P, this is point Q, and this is point R. So clearly here R is over in its gaseous state. Yeah, so these will be due, I do have hints. These will be due Friday. Weather should be fine. Might be kind of chilly. Here are my hints. You don't have to use calculator for these. I don't think you do anyway. Okay. So for this one, if you read it, it basically says hydrazine. You're like, I don't know anything about hydrazine. In fact, if you want to Google it, Google hydrazine, and you'll find it just fine. But they go ahead and they give you some information about hydrazine. So I start to draw my Y, and you can see actually I picked out the whole slope of the, and I drew it with a negative slope. Dang it. Oh, I can fix that. The fact that the liquid is less dense than the solid means that actually it's the opposite of water. So I'm going to go ahead and draw a positive slope in there. Okay. Whoops. And move my L over. And that line extends up. The abrupt end is to this one right here between the liquid and the gas. And then it goes on to give you some more information. It gives you the normal boiling point temperature. And of course, on your diagram, you need to, on the pressure, you need to draw 1 atmosphere or 760 millimeters of mercury, whichever you want. And then go over here and draw in for the boiling point would be over here, right? I drew it wrong. Be right here. And draw down here. And that would be 2 degrees. Wait, I'm getting myself confused. That would be 113.5, and this would be 2 degrees. Does that make sense? So you're just trying to recreate what we've been talking about. Also gives you that critical point, and it gives you the ordered pairs of the pressure and temperature. The next one looks like this, where A is pretty good, okay? They actually give you the phase diagram of phosphorus, and they ask you where those question marks, you know, it's like, what, liquid and gas, kind of. B, it says that when they heat it up, they say it can't be melted if it's done at atmospheric pressure. So this is kind of like the carbon dioxide. If this is 43 atmospheres, what do you think 1 atmosphere is? Okay, down here. So basically what we have going on at atmospheric pressure is sublimation. That's kind of what they're talking about there. Then the other one, and I just say make sure that you say all phase diagrams. The other one says, what's it look like if you start here at A, in this sector, which would be a solid, right? I want you to just kind of describe if you stay at the same temperature and if you reduce the pressure. Okay? Just to get you looking at phase diagrams. Then this one, actually, you need, I think, to refer to figure 1231, which is kind of this. And I don't have a lot of hints for you because I ran out of time and energy. But you should be fine. Remember, torr is the same as 1 torr is equal to 1 millimeter mercury. Okay. And so there are 760 torrs in 1 atmosphere. And then the last one is this one, where you have an assortment of gases up there, and they are actually also listed in this table, and it says, are these likely to occur? Now, you need to focus on when it says, are these likely to occur? In other words, is it likely that you will find carbon dioxide in its solid state? No, it is not likely. Oh yeah, that's right, number 50, where it says you'll use more than just this, because it says just basically use any appropriate phase diagrams. And we looked at one today that says no, that's not going to happen. Okay, so focus on, will methane be a liquid? I don't think so, but find the phase diagram. 1 atmosphere, find which sector it's in at normal atmospheric pressures and temperatures. Okay, so that's that. Any questions? Okay. So I'll post these out there, and these will be due